So, what if I told you that a 5-year-old could learn to think like a scientist? I know, it sounds like a bit of a stretch, right? But today we're going to break down a really powerful framework that makes it happen. Let's dive in.
Think about it. How do you get a 5-year-old to build a real scientific argument? We usually picture scientists surrounded by complicated charts and using all this jargon, but what if you could just boil it all down to the absolute basics of what makes an argument strong?
Well, it turns out there's a beautifully simple way to do it. It's a 3-step process: claim, evidence, and reasoning. You'll often hear it called CER. And this little trick is the key to building a logical argument, whether you're 5 years old or 55.
Okay, so let's really break down this CER framework. We're going to look at what each piece of the puzzle means and why it just clicks so well for young kids.
And the way this is taught is it's genius. It uses a traffic light analogy: red, green, and yellow, which, every kid understands instantly. Each color means do this, and each action gets its own little icon: a brain for thinking, a magnifying glass for looking, and a pencil for explaining. So simple.
First up, you have the claim, and that's the red light. It's telling the student, hey, stop, just think for a second. What's your answer to the question? What do you think is going on here? This is your starting line.
And then, boom, you get the green light. That's for evidence, and green means go. Go look for proof. What did you see? What did you hear? What clues can you find that back up what you just claimed? This is where you get out that magnifying glass and start investigating.
And finally, we hit the yellow light: reasoning. This means slow down, pause, and explain. This part is so important. It's the glue that holds everything together. How does your evidence actually prove your claim? That little pencil icon is a reminder that this is where you connect all the dots for everyone.
All right, so the theory sounds great, right? But what does this actually look like when a kid sits down to do it? Let's walk through a real classroom example.
So here we're looking at a worksheet from a first-grade class, and the question they had to tackle was pretty simple. Why does tapping on a bucket make a sound? You can see how the student went through and filled in each of the boxes, the C, the E, and the R, to build their case.
Let's follow their train of thought. First things first, they have to make a claim. They have to give a straight-up answer to that question. And there it is. The student says you make the bucket vibrate when you tap on it. You can even see how they're guided by these little sentence starters, and they picked a great science word, vibrate, from the word bank. It's a solid, clear answer.
Okay, so that's the claim. It's all about vibration. Now comes the hard part. They've got to back it up. What do they actually see that makes them think that?
And the evidence is based on something they did themselves. They wrote, I see that when I tap on something, it makes it move or vibrate. They literally tapped the bucket and saw it move. It's not a guess, it's rooted in their own personal experience.
Now for the final, most critical step, the reasoning. This is where they have to explain why a vibrating bucket even matters. How does that connect back to the sound?
And here's the final link in the chain. The student brings in a big scientific idea that vibrations create sound to explain why their evidence proves their claim. And just like that, you have a complete, logical, scientific argument. Pretty amazing for a first grader.
But you know what's really cool about this whole framework? It grows with the kids. It's not just for first graders talking about buckets. Let's take a look at how it gets adapted for different ages. Check this out. We're talking about 4-year-olds here in transitional kindergarten. The question is about healthy food. The claim? The apple is healthier. And the evidence? Simply, I see the apple as a fruit. It's so wonderfully simple, but it's teaching that fundamental structure. Make a point, then back it up with something you see. Then you pop up to kindergarten, and the concepts get a little more complex. Here, students are playing with a toy car, exploring physics. The claim is about what happens when you push it. The evidence is what they actually see the car do. It's hands-on learning plugged right into the framework.
And then look what happens by 2nd grade. Things get way more abstract. The evidence isn't even something they can touch anymore. Here, they have to use a map and a compass rose to figure out directions, and that same C.E.R structure holds up perfectly, giving them a way to organize their thoughts about more complex data.
So it's pretty obvious this is a super versatile tool. But why does it work so well? What's the secret sauce here? Let's do a quick recap.
At the end of the day, this framework does way more than just teach a formula. It builds those critical thinking muscles from a really young age. It gives kids a simple, memorable structure, that traffic light, that they can actually remember and use. The little icons and colors make abstract ideas feel real. And because it can be tweaked for different ages, it literally grows with them. But maybe the biggest thing is that it just demystifies the scientific process. It shows them that science is really just a way of asking questions and finding good answers. And that's the real takeaway here. CER isn't about filling in boxes on a worksheet. It's about teaching a mental habit, a repeatable process that a kid can take with them and use on any problem they ever face in any subject.
So I'll just leave you with this thought. A framework like this isn't about getting kids to memorize facts. It's about giving them the tools for how to think. And if we do that, if we really focus on teaching them how to reason for themselves, just imagine what kind of problems they'll be able to solve tomorrow.